Hello, everyone. My name is Yanfeng Lu. I'm a senior scientist of Oral and Language Intelligence Department at the Institute for Infocom Research, ISTAR. I have been doing speech synthesis for quite a few years. In this lecture, I will give you a brief introduction of a speech synthesis. Specifically, I will adopt a historical approach. I hope this will help you obtain a good understanding of the basic concepts and ideas of speech synthesis. Here's a lecture overview. It consists of 5 sections. In the first section, we talk about the basic task of speech synthesis. And then in section 2, we talk about the transition from mechanical to signal processing simulation. Section 3, we will talk about a paradigm shift. It's from speech action simulation to data modeling. And in section 4, we talk about the latest development of speech synthesis. At the end of the lecture, in section 5, I will talk about some future directions of the field. So let's start with section 1, the basic task of speech synthesis. In one sentence, the basic task of speech synthesis is this: let machines talk like human beings. As we all know, talking is a very unique ability of human beings. And among the intelligence of human beings, there are many aspects, but the talking belongs to the highest intelligence. Since talking is very complicated than we may first think, making machines talk is a very challenging and fascinating task. In a sense, we can say it's a dream of engineers. So let's look at how human beings talk. On the right-hand side is an anatomy diagram of the human vocal tract. This is the basis of a human speech production process. The process consists of mainly 3 stages. At the first stage, air inflows from the lung into the vocal tract. And the vocal folds will vibrate in the air. That's the second stage of this human speech production process. And then finally, the vibrated air is modified by the mouth and the nose. So this clearly shows the structure and the process of human speech production. And this is the foundation for speech synthesis. All the ideas are based on this knowledge of a human being speech production process. So we move on to the first phase of the development of speech synthesis, from mechanics to signal processing approach. So the earliest approach of speech synthesis is to do mechanical simulation. Specifically, it's a mechanical simulation of the human vocal tract and the speech production process, as we just talked about. A good example is Wolfgang von Kempelen's speaking machine. This is created in 1791. The original model could still be found in Deutsches Museum in Munich. So the diagram shows the original model and also a remodeling of the original model. So from these pictures, we can see there is a clear correspondence between the speaking machine and the human vocal tract. And the bellows on the right-hand side correspond to the lung. And the reed in the middle correspond to vocal folds. And the wind box correspond to mouth and nose. So we can see in this mechanical approach, the simulation is very straightforward. We just try to create a mechanical model of the human vocal tract. But there are some obvious disadvantages of the mechanical approach. One thing is in a mechanical approach, we cannot reach a high simulation accuracy because, as we said, the human vocal tract and the speech production process are very complicated. I mean, the mechanical model cannot get very close to the real structure and the process of human speech production. And another thing is this mechanical model is very difficult to build. And also it's very difficult to control because it's mechanics. And if anything goes wrong, it's difficult to make an adjustment. So these are the major advantages of the mechanical approach. With the development of signal processing, people find a new way to simulate a vocal tract. This new way is using the signal processing. So the basic idea is, again, to simulate the human vocal tract. But in this case, we do some functional simulation instead of a physical simulation. So the basic idea is to divide the system into source and filters. The source corresponds to the human vocal tract, and the filters correspond to the mouth and the nose. So in this particular example, Homer Dudley's Voda, which was presented at the New York World's Fair in 1939, we can see it's using electronic circuits to simulate the human vocal tract. In a diagram on the left-hand side is the source. It could either be unvoiced source or voiced source. And the source gets modified by the circuit in the middle. And finally, the modified signal goes through an amplifier to be played out with a loudspeaker. We can listen to this sample.
Will you please make the voter say for our Eastern listeners, good evening, radio audience. Good evening, radio audience. And now for our Western listeners, say, good afternoon, radio audience. Good afternoon, radio audience.
We can hear that the synthesized speech is very basic at the first stage. Another approach is to do a different kind of simulation with the signal processing. In this case, it's doing formant simulation. So this is a Gunnar Funt's OVE created in 1953. The diagram also shows the basic structure. The basic idea is still source plus filters. Both the voder and the OVE has to be operated by human beings, as the picture shows. Let's reflect on these new ways of simulation and the simulation method as a whole. So, as we mentioned, human speech production is a very complex process. It actually is much more complex than we may originally think. So, to do simulation, then there is no easy model, because the original process is very complicated. There's no easy model of this original process. And in order to do simulation, first we need to have a good understanding of the model. And another thing is to have a good way of simulating the original model. But in both respects, I mean, it's very difficult. First, we haven't got a very good understanding of the human speech production process. And also, there is no good way, very perfect way to do the simulation. And that's the basic difficulty of the simulation approach. Then we move on to the next phase of the development of a speech synthesis, which is from a speech action simulation to data modeling. This is actually a paradigm shift. It's a shift from simulation to data modeling. Essentially, it's moving the focus from speaking to speech, from action to result. So in a simulation approach we talked about just now, we can see it's trying to simulate the speech production process. That's the action, the speaking action. But now engineers are trying to do speech synthesis in a different way. They're trying to model the data instead. The data is the speech data. So it's essentially is a transition from speaking to speech. In a sense, we can say speech action simulation is also a modeling, because in the simulation, we're trying to create a model of the vocal tract and the speech production process. So this is also a modeling. It's just that kind of modeling is very difficult to realize. And if we move on to modeling the data, the speech itself, it becomes much straightforward and easier. So that's the basic idea in this paradigm shift, just to do the things in a different way and make it much easier. Then we will think, why is speech data modeling a better approach? I think there are two major reasons. First, speech data modeling is closer to target, because as we said, we in speech synthesis, we're trying to let machines to talk like human beings. So the final result is speech. So that's the target we want to achieve. And if we are modeling the speech itself directly, then we move closer to the target. Another reason is that modeling the speech is much easier than modeling the speech action itself, because the speech action is a physical process, whereas the speech data they're just the signals. So in this case, we can use a signal processing method to handle the speech directly, and it is much easier than handling the speech action. So that's these are the two major reasons why this paradigm is meaningful. It's just to make things much easier. In data modeling, the most important thing is to create the data. We need to have the data first, and then on basis of the data, we can do data modeling. So creating a speech data set is a very important stage in this new approach. So next, we talk about how to create a speech data set. A speech data set consists of speech data, obviously, and usually it consists of sentences. We just have a set of sentences in the speech data. And for each of the sentence, first we need to have the signal, which is the speech itself. And besides that, we needed to have the transcription, which is the text. Because we are doing speech synthesis, we needed to go from text to speech. We needed to have both items in this data set. Here are the 4 steps of creating a data set. First, we need to design a text first. In this stage, we needed to try to make sure that we have a good phone and phoneme combination. We needed to have a good coverage first, and then we need to have a good balance. Because a language have a set of phones. In a data set, in order to model all the phones, we have to have all the phones first. And then the phones, the data of the phones have to be good balanced The most frequent phones needed to have needed to occupy a large part of the data set, and also in the rare phones still needed to have enough data in a data set. So that's some basic principles of text design. Once we have the text, we study the recording process. And speech synthesis has very higher requirement of the recording itself. So usually we have a professional speakers record the sentences in a very professional studio environment. Again, the requirement of the final recording is very high. After the text are recorded, then we needed to do transcription. The major task of a transcription is to match the text with the signal, with the speech signal. Because in a recording, the speakers could make mistakes. So correcting errors is a important part of the transcription. Another thing is to do a normalization. We needed to turn all the symbols, non-lexical symbols, into lexical words. That's another part of the transcription. And after the transcription, we also needed to do some post-processing. Normally, we need to split the recording into standalone sentences. Because in a recording, sometimes we at once we record many sentences together. And finally, we need to split all the recordings into sentences. In this phase, we also need to remove some flaws in a recording and clean some flawed recordings. And finally, we need to label all the sentences well in order to facilitate the processing afterwards. So these are the 4 main steps of building a data set. And this is the foundation of the data modeling approach. Without the data, we cannot do any modeling. Let's talk about a major a core part of speech synthesis. As we said, the basic task of speech synthesis is to let machines talk like human beings. So talking is one thing, and it's very complicated. So engineers trying to limit the task first. This is the task of text to speech. So text to speech compared with talking is a little bit similar because it's just reading text aloud. Reading is a simple task than talking, and text to speech has been a target for speech synthesis for a long time. And we can see in this focused task, the core problem is to do a mapping. Specifically, it's mapping a text to speech. And if we look closer, we can see it is a sequence to sequence mapping because both the text and the speech are sequences. So we map one type of sequence into a different type of sequence. So that's the essential task of this focused task. Another important thing for speech, for text to speech, is that compared with the previous approach, it has to be automatic. As we see in both the 2 examples of signal processing simulation, the VODA and the OVE, those devices had to be operated by human beings. But in this case of text to speech, the system has to run automatically without any human intervention. So that's a different, that's another important difference between this new approach and the previous approach. So we know the basic task, the core problem of this focused task, which is text to speech. And basically, it's a general mapping from text to speech. But again, this task is very complicated. So The engineers adopt a very common approach to this basic task. And this approach is divide and conquer. When we face a very complicated task, a good approach is to do divide and conquer. So the core mapping problem is mapping text to speech, and that's very complicated. But we can do it in several steps. We can divide the general mapping from text to speech into different submappings. Specifically, we can map a text to phone sequence first, and then we map a phone sequence to acoustic features. And finally, we map acoustic features to waveform. So these are the three submappings engineers adopted in tackling the general problem of text to speech. Based on this, we have the basic architecture of a TTS system. This diagram shows the three main parts of a typical TTS system. It consists of the front end, the acoustic model, and finally the vocoder. These three components just corresponds to the three submappings. So the front end maps text to phone sequence, and the acoustic model maps the phone sequence to acoustic features. And finally, the vocoder maps the acoustic features into waveform, which is essentially the speech itself. So next, let's take some closer view of those three major components of a typical TTS system. First, let's look at the front end. So the basic task of the front end is to map a text into phone sequences. Several tasks are involved in this front end component. One thing is to do segmentation. The input to the whole TTS system is text. Normally, it's a long paragraph of text. So when we get this long paragraph of text, we need to segment the text into text unit. And apparently, punctuation is a good break to be used to segment the input text. After the input text is segmented into different units, then we needed to do normalization. So normalization means converting non-lexical symbols into lexical words. In a free text, we often have non-lexical symbols such as numbers, time and date, ratio, percentage, abbreviation, etc. All these non-lexical symbols have to be converted into words in order for the TTS system to process it. So that's the task of normalization. Another task of text processing is to do disambiguation. Because some of the symbols in the text could be ambiguous. For example, the sequence 1820 could be read in different ways. It could be a year, which should be read as 1820. It could be a number. In that case, it should be read as 1820. So for a different meaning, it has different pronunciation. Another example is the sequence DR dot. I mean, it could also have two different meanings. It could be an abbreviation for doctor, or it could be an abbreviation for drive. So these are very typical examples of ambiguous symbols, and these has to be disambiguatized in order to for the TTS system to read it properly. Besides the three tasks, there are also word segmentation. This applies only for special languages such as Chinese, because in Chinese, the words are not separated naturally by space. So we needed to separate the word to do a word segmentation. For this special case, such as Chinese. All the previous tasks are based on the words. So beyond that, the TTS front end could also do some high-level analysis. This is a syntactical analysis. One task is to do a part of speech analysis. So for each of the word, we need to identify the part of speech of that word. So this is called POS tagging. And further, we could construct the syntax, the tree for a whole sentence. All these will be a good guidance for speech generation. Another important task for the front end is to do grapheme to phoneme mapping. This is abbreviated as G2P. So normally, we use a dictionary to do this kind of mapping. For most of the word, we just go to the dictionary and check the phone sequence for that particular word. But for some languages, like English, very often we will run into words which are outside of the dictionary. So these are called out of vocabulary words. For these words, we have to have a way to map it into its phone sequence. We needed to adopt a different approach than dictionary because these words are not in a dictionary. Another important aspect is to handle the polyphone. Polyphone is the phenomenon of the same phoneme is read differently. A good example is project and project, or lead and led. So they have the same grapheme. They have the same sequence of letters, but they could be read differently in different contexts. So these are examples of a polyphone. This kind of words also need to be handled by the front end. So based on these tasks, we have a general understanding of the things which are done in the front end of a TTS system. Then we move on to the second component, which is the acoustic modeling. A typical approach is to use a hidden Markov model to model the acoustic features. But as we know, the modeling power of the hidden Markov model is very weak. So we can only model a phone with the hidden Markov model. And beyond the scope beyond the phone is very difficult. It's beyond the modeling power of a hidden Markov model. Even for a phone, it's still difficult for hidden Markov model. So in this case, we have to do further divide and conquer. Specifically, we divide the modeling of a phone into two parts. One is the decision tree, and the other one is to do the real hidden Markov model modeling. So let's look at the details of how we do this kind of further divide and conquer. First, let's look at the decision tree. So the basic task of a decision tree is to cluster phones on the basis of linguistic context. So in the front end, we map the input text into phone sequences. But for each of the phone in a sequence, we also compute its linguistic context. And the decision tree is to group phones together based on these linguistic context. Why are we doing this? The basic assumption is that phones in similar contexts are read similarly. So if we group the phones based on the linguistic context, then we can put similar phones in a same group. This just make the modeling much easier after this. And the typical context features included these. First, the phone ID itself. We need to know what kind of phone is this. And then we also consider the neighboring phones. And besides the phone IDs, we needed also to consider other phonetic features, such as, is it a vowel, is it a nasal, is it an accented phone, and what's the position of this phone in a word. I mean, all these phonetic features will influence the pronunciation of the phone itself. And on higher levels, even syntactic features have an impact on the pronunciation of this particular phone, such as the parts of speech and the word position in a phrase and also in a sentence. So all these are linguistic factors which have an influence on the pronunciation of a particular phone. So all these have to be considered in modeling the phone. And the basic task of the decision tree is to cluster the phones based on these linguistic context. Here's an example of a decision tree. Basically, we just ask, based on the linguistic features, we ask all kinds of questions. For example, in this diagram, first we ask the question whether this phone is a vowel or not. So based on that, we go to different branches of the tree. In creating the decision tree, the algorithm follows a basic splitting criterion. It's called a minimum description length. The basic idea is to make the tree as balanced as possible. So we don't want to have a tree that is unbalanced. That will make the depth very deep. So with the balanced tree, then we can have a very shallow tree and make the clustering process easier. So that's the basic criteria in constructing a decision tree. This diagram shows how we do a hidden Markov model, phone model. We can see in a hidden Markov model, we have different states. So for each of the phone, we will have several states. We're using the states to model a phone. So this diagram shows the correspondence of the hidden Markov model and the phone. Basically, for each of the phone, we have a model, and the state corresponded to a segment of the phone. And in terms of acoustic features, these are the features usually used by engineers. The first is the spectrum. Normally, people are using male capstrum, and the window of shift is normally 5 milliseconds. Besides the spectrum, engineers also use log F0 to modeling the phone. And these are the basic features, acoustic features. On top of that, people are also doing velocity and acceleration. What does this mean? A velocity is defined by the difference of 2 consecutive frames divided by 2. So for any of the basic features, we just do a difference between 2 consecutive frames and then divided by 2. And then we have the velocity feature. So this is a high-level feature based on the basic features. And the acceleration is, again, based on velocity. I mean, the algorithm is similar. We just have the difference of the velocity of 2 consecutive frames and then divided by 2. So then we have the acceleration. So velocity and acceleration are higher level acoustic features based on the basic acoustic features. Duration is a very special thing than the normal acoustic features, because the acoustic features are frame level features. In spectrum and F0, those are all features of the frame. But duration is not a frame level feature, it's a state level feature. A state could consist of several frames. So the duration is a different level of features, and it has to be modeled separately. So the HTS, which is a hidden Markov model based TTS system, the essential idea is to do a statistical modeling. In this statistical modeling, we use the probability density function as the observation of the hidden Markov model state. So the state actually, the output of the state is the PDF of a particular feature, of a particular acoustic feature. And since spectral parameters are continuous, in this case, we can just use one single PDF to model it. But for log F0, the case is more complicated because it's intermittent. For some of the frames, the log F0 could be undefined. So in that case, we cannot use just one single PDF to model it. We needed to use multiple space PDF in this case to model log F0. And for different space, we needed to assign weights. So the weights itself themselves are also part of the model. So generally, in the Markov model, we are doing a statistical modeling. We are modeling the probability density function of a particular acoustic feature. And then finally, we have all these particular HMM parameters. Basically, we have first the basic features, including the spectrum part and also the F0 part. So all these, again, those are in a hidden Markov model, we are modeling the PDF function of these features. And based on these basic features, we also model the velocity and the acceleration of the basic features. So finally, we have this list of the parameters which are modeled in a HTS. Again, duration is different than these features, these frame level features. Since this is a state level feature, it has to be modeled separately. So here we have a general idea of all the models in a HTS system. I mean, these are all the things we needed to model in a HTS system. These are all the acoustic features. If we put the two parts we discussed just now together, then we have a good understanding of how a HTS system works. Basically, it does a further divide and conquer in acoustic modeling. We can see the acoustic modeling is divided into decision tree and the actual HMM model. The decision tree clusters similar phones together based on their linguistic context. So finally, on the leaves of the trees, we'll have different clusters. And for each of the cluster, we do HMM modeling. So this diagram clearly shows the divide and conquer approach in this particular acoustic modeling. Then we reached the third part of the TTS system, which is the vocoder. Vocoder is an abbreviation of a voice encoder. Its function is to map waveform into acoustic features and also the other way around. So this is bidirectional. not just from one sequence to another. It's actually a bidirectional mapping. Actually, both directions is used in building a TDS system. The mapping from waveform to acoustic parameters is used in the training process, and the mapping from acoustic parameters to waveform is used in speech generation. So vocoder is a very important component in the TDS system. An alternative to HTS, the hidden Markov model-based TDS system is a concatenative TTS. And the idea is very different than HTS here. The basic idea of a concatenative TTS is to generate a speech based on concatenating recorded speech. So that's the basic idea of a concatenative TTS. Here we needed to make sure we know the difference between concatenative TTS and the canned speech. In a canned speech, we record very often the whole sentences together, the whole sentences, and use the whole sentences as a whole in a final product. And for some of the sentences, we might only replace a small part of it. A good example is the station announcement system on MRT. We are listening. We hear all those announcements every day on MRT. We can see that the major part of the final speech, they are pre-recorded. It's just for different stations. I mean, a small part of the final speech is replaced with that particular station. So that's a good example of a canned speech. A concatenative speech is very different because it has to handle free text. I mean, the input of the canned speech is a limited set. You can only announce a certain number of stations. If you have a new station, then you needed to do a new recording. But for concatenative TDS, we don't need to do new recording. It takes free text. You can input any text into the system. So that's the major difference between a concatenative TTS and a canned speech. Because it has a different task, in concatenative task, we have to use a much smaller unit. We cannot use a whole sentence or even a phrase as a unit of concatenation. We have to move on to a much finer unit. Normally, we're using phone or diphones. Only by using this much smaller unit, we can achieve this kind of free text synthesis. Actually, before HTS, a concatenative TTS already existed. But in that phase, the concatenation is very limited and simple. Even in a concatenative speech, where a TTS system, we only include typical units. So normally for a language, we just record the phones for each of the items in the phone set. So that's the early phase of concatenative speech. And not just the database is very limited. We only include typical units in a database, but also in a final speech, we are we're heavily using signal processing methods to process the final speech, because the unit is very limited. we'll have to do heavy signal processing in order to make the final speech smooth. So that's the phase before HTS. But after HTS came out, people still developed the concatenative approach. Then what's the reason for that? And the major reason is that the parametric speech synthesis, like HTS, it can only generate a very robotic speech. And the major reason is that the hidden Markov model has a very limited modeling power. And also the vocoder in the mapping from acoustic features into wave samples is using signal processing method. So these are two reasons decides the poor quality of the HTS system. We can listen to a sample here. So this is a sample generated by HTS system. We can feel that it's very robotic.
This is a sample speech generated with a hidden Markov model-based text-to-speech system. You can hear that the voice is rather robotic. The reasons are mainly twofold: the weak modeling power of the hidden Markov model and signal processing methods being used to generate the speech.
So we can hear it's very robotic. So because of this lower quality of the generated speech from HTS system, engineers are developing the concatenative model even after the HTS. Well, the new development mainly are reflected in a new way of doing the concatenation. Originally, the concatenation only based on a limited set of units, and also signal processing are heavily used. But in this new approach, both aspects were changed. Let's look at the details of this new approach of concatenative TTS. So, and the core idea behind this new concatenative approach is the unit selection. So in the previous concatenative TTS system, we only have a limited set of units. We don't have we cannot select from the unit. I mean, for each of the phone, we only have one candidate. But in this new approach, we have thousands of candidates for a particular phone. So that's the basic idea of this new concatenative approach. This new idea of unit selection is presented in Hunt and Black's seminal paper in 1996. So the basic idea is to have a large unit database. And the unit database contains both the waveform and the features, and all kinds of features. Could be linguistic features, could be other features. And the important thing is for each of the unit, I mean, normally it's a phone. There are many candidates. It could be thousands of them. Hence, we have the task of unit selection. We need to select a good candidate, the best candidate for a particular unit. So for a free text input, first, in the front end, we map the input sentence into a phone sequence. And that's a unit sequence. And then for each of the units in a sequence, we need to decide which is the best candidate of this particular unit. So that's the core task of unit selection. For each of the unit, we select the best candidate from a very large unit database. In order to do unit selection, we need to follow some specific algorithms. So the most important thing is to follow a criteria of selection. And two costs are proposed in that seminal paper. One is the target cost, one is the concatenation cost. The target cost reflects the distance between a candidate unit in the database and the target unit in the input sentence. So the unit database contains all the unit candidates with their features. And based on the input sentence, we can also generate a unit sequence with their features. And we can calculate the distance between the candidate and the target based on their features. So that's the target cost. And besides this, there's the concatenation cost. So the target cost is the relation between a candidate and the target, whereas the concatenation cost is the relationship between consecutive targets. So when we choose the unit, we not only have to consider the distance between the target and the candidate. We also need to consider the distance between the relationship between the candidate, the consecutive candidate, whether it will be awkward if we put the two units together. So the concatenation cost is a reflection of this awkwardness of consecutive units. And major factors to consider is fragmentation. If it's fragmented, then the final speech won't be smooth. And also we can calculate the boundary distance. So when we put the two units together, we can calculate the boundary distance based on some features. And the general criteria is to combine these two costs together. So in selected units for target input, we needed to minimize the total joint cost across the whole sentence. So for each of the unit, it has a target cost and a concatenation cost. We need to add all these together and also add all the costs of the units in a sentence together. So that's the total joint cost across the whole sentence. So the goal is to minimize this total cost. So that's the criteria of a unit selection. And then in terms of the algorithm, how do we achieve this kind of, how do we follow this criteria? I mean, that's the algorithm of doing this unit selection. We can see unit selection is essentially a search problem. Basically, for each of the units in an input sequence, we need to select, we need to search the unit database to find the best candidate. So this is a search problem. But if we do brutal search, that would be too expensive. For example, if we have only 10 units in a sentence, and for each of the units, we have 1,000 candidates. If we do a brutal search, then the search space is very huge. It's 1,000 raised to the 10th power choices we need to choose from. So that will be a very expensive search. So in order to do a practical search, we need to follow some heuristics. And the solution is Viterbi search with pruning. Pruning means we don't search all the space. We just search a limited part of the space. So and this is reflected in the concept of pre-selection. So even for a particular phone, I mean, we don't take care of all the candidates for the phone. We don't pick all the candidates. So for each of the phone, from all the candidates in the unit database, we only pick the k best candidates. That's a pre-selection and also a way of pruning. We don't need to consider all the candidates together to put in a sentence. First, we just choose the k best candidates for this particular candidate to consider. the key best candidate to consider. And then based on these pre-selected units, we do a Viterbi search. The idea of the Viterbi search is to build the sequence unit by unit. And on the way, we only keep a certain number of best paths. We don't keep all the paths. We only keep the best n paths at each step. So with both techniques, we greatly reduce the search space. We make the search job very practical, very efficient. Certainly, it won't be perfect. I mean, a perfect search is to search all the space, but we cannot do that because it's very expensive. Then we just do a very practical search, make it very efficient, but it's still very effective. I mean, it cannot be guaranteed to be perfect, but it's the most effective search with a limited amount of computation. So that's the basic idea of this Viterbi search with the pruning approach of unit selection. With all the units selected, finally, we still need to do the concatenation. This phase is very easy. We just put all the phones together, but we cannot put those phones together directly. We needed to do some very easy smoothing technique. Usually, crossfading is used for this smoothing purpose. But compared with the original signal processing methods, this is really easy. We just do a very easy crossfading to make the final speech more smooth. It's essentially just to put all the units together. So this last phase is very simplified compared to the original concatenation, which requires a very heavy signal processing. Okay, we talked about two ways of doing building a TTS system, and the hidden Markov model based TTS system and the concatenative TTS. Now we can do a comparison between them. To build HTS, first we needed to analyze the speech data into acoustic parameters, and then based on the acoustic parameters, we do the statistical modeling. This is actually acoustic modeling. And in a synthesis part, we just use the acoustic model to generate the acoustic features first, and then use the vocoder to generate the speech. This is the basic way of doing hidden Markov-based TTS system. The concatenative TTS is a little bit different. In this case, we need to build a large unit database first. The database contains all the units, usually it's phones, all the phones with their linguistic and acoustic parameters. And finally, we use unit selection to generate the speech directly. So in this case, we can see there is no vocoder involved. We don't need a vocoder because we just put all the recorded speech together. We concatenate the original speech together. In this case, we don't need a vocoder. We are not using statistical models of the acoustic features. So these are two different ways of building a TTS system. But both are based on speech data. So it belongs to the same paradigm, but different approaches. And in terms of quality, HTS is robotic, as we heard before, and concatenative TTS is more natural because it's based on natural speech. But the disadvantage of concatenative TTS is that it's not very smooth because we put all the units together, and those units could come from very different sources, and that makes the generated speech more natural, but not as smooth as the speech generated by the HTS system. And in terms of the resource, HTS is very lightweight because you don't need this huge unit database, whereas concatenative TTS is very huge, only because the unit database is very huge. We can listen to the samples from each of these systems and compare the quantities of the generated speech. So this sample we heard before, let's hear it once more.
This is a sample speech generated with a hidden Markov model-based text-to-speech system. You can hear that the voice is rather robotic. The reasons are mainly twofold: the weak modeling power of the hidden Markov model and signal processing methods being used to generate the speech.
And this is a sample generated by the concatenative TTS system.
This is a sample speech generated with the concatenative text-to-speech system. You can hear that the voice is much clearer than those generated with the parametric system. But it's not smooth. This is caused by concatenating units that come from rather different original contexts.
So these two samples clearly shows the different aspects of these two approaches of building a TTS system. With the advantages and disadvantages, I mean, engineers are thinking, why can we combine these two systems together? So in that case, we can take advantage of all their good aspects, but try to, at the same time, try to avoid their flaws. So comes the hybrid approach. In a hybrid approach, we just combine these two TTS systems together. The basic idea is still the concatenative TTS. So we're doing unit selection. It just in doing a unit selection, we use the acoustic models as part of the criteria. So that's the key idea of doing this kind of hybrid TTS system. So we just use the acoustic models that are used in a HTS system to guide the unit selection in a concatenative TTS system. In this way, we combine these two systems together. So these are all the major systems before the advent of a deep learning approach.